So good evening everyone. Let us get started with the discussion on dynamic equivalent circuits of a DC machine that we have started. So we have briefly looked at the DC machine magnetic field, what happens if both the fields are excited, and we understood what we mean by a model of a physical system. So if we have a physical system, if we have a set of mathematical equations, the equation 1 to n, if we have a set of mathematical equations, then the set of equations actually represent the represent the model of the system, mathematical model of the system. And for electrical engineering, especially for electrical engineering, because we are more conversant with circuits, so all those equations can be, if we can manipulate them to represent the same phenomena in form of circuits, in form of some circuits incorporating some resistance, inductance and capacitance. Then this represents the equivalent circuit model of the physical system. So this is the physical system which has certain inputs, which has certain output. So the equations represent the same thing, that the physics of this physical system can be if it can be captured by a set of mathematical equations, then that is the mathematical model. And if the mathematical model, the equations can be represented with some equivalent circuit, the equivalent circuit will also have some input and some output, like in terms of voltages and currents. So it becomes the equivalent circuit model of our physical system. So also we told that in this step from this physical system to this set of mathematical equations require some assumptions and certain approximations. So when can we say that our model is good? When a model is a good model, when we make reasonable approximations and assumptions such that if we have a set of inputs, say a set of inputs, that set of input gives some set of output. We may have different set of input, each one may correspond to output. If those can be reasonably matched with this mathematical model, that is for a wide range of input and output, for a wide range of uh, uh, wide range of operating conditions, if our mathematical model can represent the physical system accurate enough, then we can tell that that is an accurate model of our physical system, and our modeling is good enough for other purposes. Then we understood, if we once we tell about the DC machine steady state model, we understood that steady state models, we remove all the dynamics involved. So these are the steady state governing equations. This can be rewritten like this, where the speed and the torque are the important quantities, and Va is one of the variables which is within our control. We can change that armature voltage that we apply, and we have different sets of motor characteristics. And if we superimpose the load characteristics, that is the relation between the speed and load torque for our load, if we superimpose the load characteristics on the motor characteristics, then the intersection points indicate the steady state operating points. We discussed that the steady state model can reasonably tell us these steady state operating points reasonably well, but they cannot tell about the dynamic behavior. Suppose what happens if the motor, if we have been applying 80 volt, now suddenly we have, and the motor is operating at this point, at this speed and at this torque. Then what happens if we suddenly reduce the voltage to 40 volt? We know the steady state model tells us that yeah, it will come back to this point, but it does not tell us what trajectory it takes, or how the operating point shifts from point 1 to point 2. And this information is actually useful if we want to uh, if we want closed loop control. For closed loop control, we need to have the dynamic model of any system, so that we can do controller design, and that will enable us to control the dynamics. Say we want the speed from n1 to n2 within this much seconds with no overshoot. It should not go higher and then come back. It should go straight away like this. It should not go, suppose we want n1 to n2, the actual speed should not go like this. Let us say it I want, or it can be very slow like this. We want it reasonably fast, but with reasonably low overshoot and no overshoot. That may be, those may be the different requirements. So if we want to design a controller for that, we require the dynamic model of the system. So that is why the discussion on dynamic model is important. So what are the different dynamic elements, dynamic circuit elements? One is the inductance, one is capacitance. We understood what we mean by them. Resistance is basically the power dissipation or in a power conversion from basically energy conversion from one form to another, electrical to mechanical. That can be represented by resistance. Electrical to heat, that can be represented by resistance. So wherever we have some active energy dissipation, that phenomena can be represented with resistance. Inductance represents the magnetic field energy stored in magnetic field, um, and capacitance represents energy stored in electric field. So if we have a coil, we understand that we have lot of flux lines flowing and we have some B distribution. That means we have some inductance or some magnetic energy stored. That indicates that this coil has certain inductance. We understood that, yeah, we understood self inductance, that is inductance of the coil due to, or the energy stored in the vicinity of the coil due to its own current. When the current of the coil itself produces the magnetic field, and that gets or the flux that produces certain flux, and that flux links the coil, that is that ratio of flux linkage to current, that is known as the, or defined as, the self flux linkage. Then we understood about mutual flux linkage. So if we have current in some winding, say I1, that produces some flux psi1. Part of that flux or the complete flux links the another flux, another coil, say coil 2, and the flux linkage is psi2. Then the ratio of psi2 to I1, that is the mutual inductance of the between these two coils. And oppositely, if we inject some current I2, then it will produce some flux linkage psi2. Part of that flux linkage psi1 will link the first coil. So in this case, psi1 by I2 will be defined as the other mutual inductance, and we discussed that those come out to be the same. Uh, the mutual flux linkage from coil 1 to coil 2, and mutual flux linkage between coil from coil 2 to coil 1. They if we do the math, they come out to be the same, and same is equal, the number comes out n1 n2 divided by the reluctance of the flux path. And again for the self flux linkage, the number comes out to be, say n1 is the number of turns, so n1 square divided by reluctance of that flux path, that is the self inductance. And mutual inductance is n1 n2, where n1 is the number of turns in the first coil, n2 is the number of turns in the second coil. Reluctance is the reluctance, or the flux path, mutual flux path, whatever is the reluctance, that is that we have to put this that reluctance here, and this comes out to be the mutual inductance. So you understood mutual flux linkage and mutual inductance. Now we know that there are two coils in a DC machine. We have a field winding and armature winding. So if only the field winding is excited, you can see that lot of flux lines are there, and obviously there's going to be some inductance or some energy storage first of all, then some flux linkage and some inductance also. So say the field winding has some inductance LF, and similarly the armature winding, that also if only that is excited, then we have already understood the flux line distribution. And because there are some flux lines distributed, there is some B distribution, so there will be some energy stored, and that energy stored will lead to some inductance. And let us say we define that inductance by armature inductance La. Now which one will be higher, which one will be lower from the magnetic circuit uh, represent or the magnetic circuit uh, a magnetic flux line distribution only we can reasonably tell that. So you can tell that along the axis of the magnetic field in the field winding, you have air gap to be quite small. You have we discussed elaborately last time what we mean by the effective air gap in this case, and how do we actually what we actually mean by reluctance when how are we comparing this to reluctance, what do we mean by that. So if we take a small strip with cross sectional area dA, then if dA remains reasonably same everywhere, then we can simply compare the length of the flux lines and conclude which one is going to be higher, which length is higher and which length is lower. So we can see for the field winding that no matter which small dA we take, we can take a small dA here or small dA here, the length of the flux line always is equal to the small gap G. But here if we take a small length here, flux line length is so big, it is so big, it is so big, it is big everywhere. So that is why we can directly compare the effective lengths of these two flux paths, and we can see that the field winding flux path length through the air gap, that is small, but for the armature winding it is big. That means whatever is the effective reluctance seen by the field winding Rf, and say the effective reluctance seen by the armature winding Ra, because Ra has involves a longer path through air gap, so it will have very high value compared to Rf. Now we define the, say, Nf is the number of field winding turns, Na is the number of armature winding turns, and the self inductances are Nf square by Rf and Ns square by R reluctance A. For now, let us consider that Nf and Na, we assume them to be same. Even if they are same, then this relationship tells us that Rf is very low compared to Ra. That means Nf 1 by Rf is very high compared to 1 by Ra. That tells us that inductance of field winding is always very high compared to inductance of armature winding, even if we consider the number of turns to be reasonably the same. Now we made some discussion on field winding, and we made some discussion on the armature winding. And
Sir, excuse me.
yeah, you have any question?
Sir, actually from reluctance, reluctance is proportional to 1 by mu naught mu r into L by A, right? Could you please comment on mu r, please?
We are discussing about the armature. We are discussing about the air path reluctance, not the iron part. So mu is always mu 0,
Okay,
because iron part relative permeability is quite high, so that does
okay.
not contribute to the overall reluctance of the magnetic circuit. So if you compare, if you do
Yes, sir.
some
Yes, I
simple
remember.
math,
I remember from
yeah,
the class.
yes, so if we have say a e core like this, if we take some, you must have done this
Yes, sir. Yes, yes.
calculations in your basic electrical engineering also. So they say you have some lengths, part of that length, a small portion is through air gap. If you actually calculate what is the reluctance due to iron, what is the reluctance due to air gap, you can simply compare their relative values. So
Yes, sir.
while discussing the inductance,
Reluctance due to air gap will
yeah,
dominate there.
yeah, that dominates very strongly. That is why we are discussing the air gap reluctance only. We are
Okay,
completely
okay. Got it,
assuming
sir.
the iron reluctance for all these discussions, and you can see that they do not matter also, unless we go into saturation where mu r value actually drops. If our machine is reasonably unsaturated, that is we are operating in the below the
Below
knee region of the
Mimax
pH
point.
curve.
Yes, yes.
If we are operating below this point, then for all practical cases, the reluctance due to iron can be safely neglected. There is no harm in that.
Okay, sir. Thank you so much.
Okay. So let us get started on the discussion. So last day we discussed on the field winding and armature winding. So field winding we have some number of turns, say NF. We have some allowable current, say IF, and on the armature winding we have some number of turns, say NA, and some current IA. And we had some discussion, and from the point of sensitivity to of torque to current, we concluded that if we have so suppose we change torque by changing current only, we are not changing the flux. So torque is K into flux into Ia. K and phi are reasonably constant, and we change torque by changing Ia directly. Suppose we have designed our machine to operate from some 0 Newton meter to 10 Newton meter. So if for from the control perspective only, what is beneficial? if we have if we have more, so if we change the current by some delta I, if that corresponds to delta t, and if this delta I is changed by changing some delta v, say we can change delta v with only say 1 volt. That is the minimum change that we can do. And if the corresponding delta I is say 1 ampere, if this 1 ampere change corresponds to 10 newton meter difference, so we cannot control the torque at all in between this range. We cannot actually have 5 newton meter torque produced out of this machine, provided our minimum voltage change that you can do is 1 volt, and the corresponding current change is 1 ampere. That is the argument that I am giving. On the other hand, if we say these values remain the same, say 1 volt is the minimum delta V that we can have, and the corresponding delta is 1 ampere instead of 1 ampere, and so this remains the same, but 1 ampere change corresponds to only 1 newton meter torque, rather than uh, this 10 newton meter 10 newton meter of torque. That means we can change the current, and we can change the current from 0 to 10 ampere, and vary the torque from 0 to 10 newton meter. So we can have more sensitivity, we can have more resolution in the torque control that we want to do. So that is one of the points that tells us that actually comes as an advantage, that okay, if armature current we have quite big armature current, then we can control torque. We have more range in current, so we can precisely control torque. But also, if we come from a design perspective, so let us try to come from a design perspective that will be more mathematical, and that will clearly tell us that why actually we need to have what are the relative values of currents and field winding number of turns for these cases. Let us try to come from some mathematical equations, and let us try to
Sir, one question I have.
formalize that. Yes.
Sir, why you are thinking like flux also we can change? Why you are keeping it almost constant, may I know?
Because flux, if you want to change, it will be slower. If once you plug in some real values, you will get. So whatever is the time constant
Okay.
for field winding, whatever is the time constant of field winding, that will be quite small or quite big compared to the time constant of armature winding. So field winding will have quite high time constant, so it will be quite slow. Even if you want to change flux, that will not change very rapidly. So that is why generally
Okay.
field current control is only done to go into uh, demagnetize or that what is that called, mm, if you want to go beyond the base speed, if you want to go higher than the
Flux
speed.
weakening, flux weakening.
Flux weakening, yeah, flux weakening, we generally then only we tend to go towards lower currents. Now let us try to come from a mathematical framework to conclude on why should we have lower field winding current and higher armature winding current. Let us try to start from, say we have discussed on, we have designed this machine, we have decided on, some air gap. We have decided on some air gap length, that is mostly decided based on some mechanical constraints of our manufacturing. And say we have discussed that in this, under this pole, what is the flux density that we want. Say we have decided on these quantities. So if we have decided on the maximum flux density and G, then obviously we have decided on the flux that we have, and because the areas and other things are constant, so that means the total mmf, say mmf equal to Ni. If B is fixed, G is fixed, then obviously H is fixed, and if H is fixed and G is also fixed, then H into G mmf, that is also fixed. So if F equal to Ni, that is constant, so F is constant as soon as we have fixed some B and G. That is, I think, clear. Now what is the relationship between current and number of turns? So say we have number of turns as n, right? And say yeah, that is n, and current, uh, and so F equal to n into I, that tells us that I equal to n by F. That is the current relationship between current and number of turns, where F is constant. Now what is going to be the winding resistance? We will now go into winding resistance. Winding resistance is nothing but rho into L by A. So first thing, L depends on the number of turns that we have, so L is proportional to N. And cross sectional area, A in this case where I am writing as capital A. So A is, what is A? A is current by current density. So J is the current density. So A, the winding cross sectional area, or cross sectional area of each turn, that is I by J. So that is the next thing. So if we plug in these values here, L is proportional to, so this will be proportional to N divided by I by J. So the uh, resistance is proportional to N into J by I, right? N into J by I. So resistance is proportional to N into J by I. Now when we are pushing this much amount of current, obviously we have some voltage constraint also, because voltage constraint will come from the supply voltage that we have in our at our disposal. That is we can change that, but once we fix that, we cannot, we the maximum voltage that we can apply, that is not, we cannot change that. So voltage, because we are now discussing on DC machine, so voltage, that will be simply R into I, whatever winding we discuss about. Say let us start discussing about field winding only. Obviously we will have some back EMF for DC machine, we will understand, or the armature winding, we will discuss that also. So voltage is basically I into R, and that is proportional to, R is proportional to N into J divided by I, and I comes here also. So voltage is simply proportional to N into J. That comes as another thing. So that tells you that N is proportional to J by V. So if V is constant, if V is fixed, next thing is if voltage of the winding that is fixed, then N is proportional to J. So that means if we
Sir, N is inversely proportional to J.
no, N is proportional to J. The upper one is J and lower one is V. V is constant, so N is proportional to J.
Sir, from the equation which you have highlighted, V is proportional to NJ, right?
Correct. So if,
From the
oh sorry, if what is the mistake that I have done here? N equal to, sorry, V by J. Sorry, N equal to V by J. That means that is correct. If V is fixed, then if we increase the current density, then our number of turns will get decreased, and if we reduce the current density, then our number of turns will get increased. So that is what is coming from the voltage constraint. Now there is another constraint is there, that is the volume that is available for putting the copper. So volume
Sir,
of
could you
copper,
please review this part once? This one.
till now.
Yes, sir.
Okay, so I'll just discuss the copper volume and then I'll discuss the whole thing once more.
Okay,
Okay,
sir. Okay. Okay. Okay.
so voltage of copper is the usable the area available to put the copper. So that is obviously that is related to the length of the so volume of copper is nothing but the length of the copper line and the cross sectional area L into A. Now L, we have seen that L is proportional to N, number of turns that we have, and A is proportional to I by J, the next thing that we have discussed. So if we simply put it, so it is proportional to N and A is proportional to I by J. So volume of copper, that is basically Ni, that is again a constant, Ni equal to F. So F by J. So volume of copper, that is inversely proportional to the current density. That is another relationship that we have obtained. Now always we will the copper loss will be another thing. I will be discussing the copper loss and then we'll be reviewing the all the things step by step. So copper loss will be another thing. So copper loss equal to I square into R. So I square into R, that is so what is I? That we have I is basically
J into A.
uh, I equal to, we'll try to represent them using some constants. So I equal to which one do we use? So resistance, let us first put the resistance. Resistance is proportional to N into J by A I, this thing. R is resistance is proportional to Nj by I, we'll put that. So this is resistance and I is I square. So one I gets cancelled, we only have one I left. So we finally have N into I into J. So that N into I is nothing but F. So F into J. So we have power loss proportional to the MMF and multiplied by J. So this is the next key equation that we have got. Now I will revisit the whole thing once more. Suppose we have decided on the flux density that we want to have in the air gap, that is the B is fixed, and we have some fixed G, the air gap length that we have, right? So B and G, those are fixed. As soon as B is fixed, because in air gap B is nothing but mu naught into H, so if B is fixed, we know H is also fixed. and if h is fixed, then h into length of the flux path to the air gap, because we are talking about the we are talking about this portion where we have overlap, so flux line length is simply g. So h into g, that is nothing but the mmf, and so mmf is also fixed. So mmf is fixed, F equal to, and mmf is nothing but number of turns into current. So F equal to Ni, that is constant as soon as we decide on some B and some G. So this is first equation, first important equation that we have. From this equation we can derive that I is equal to N by F. So for F mmf to be constant, then current and number of turns, they are proportional to each other. Current and uh, current and, sorry, here also I think I have made a mistake. So I will be equal to F by N. This will be F by N. So for a fixed mmf, current and number of turns, they are inversely proportional to each other, inversely proportional to each other. That is what this first equation tells us. Now let us try to, this is the first thing that we have. mmf, no matter what other thing happens, if we are fixed on B, if we are fixed on G, that means our mmf is fixed. That means N into I is fixed. Now let us try to discuss about resistance. Resistance of the winding is nothing but R equal L, the length of the winding. That depends on how many number of turns are there. So because the number of the length per turn, once this dimension is fixed, the length per turn is fixed. That is why the length is simply proportional to the number of turns that we have. This one, so Roman 1. And cross sectional area, that is nothing but I by J. If current density, we assume that current density, we have some current density, then cross sectional area of each where is A, and that is equal to I by J. That is the second Roman 2 that we have. If we put this Roman 1 and Roman 2 into the resistance equation, then we get this second equation where resistance is proportional to N into J divided by I. Right, that is the second equation that we have. Now we have some voltage constraint also, because we have some supply, we have to supply the winding from some voltage source, and once we decide on the voltage, we cannot go, once we have selected a voltage source, say we have selected a voltage source of 230 volt or 200 volt, no matter what, we cannot go beyond that voltage, and the windings, they have to be insulated. So once we decide on the voltage, we decide on the insulation class also, insulation class of the winding. So we cannot exceed that. So voltage is always a constraint. So say we have, so for these cases like DC machine, especially field, we can simply represent the voltage as IR drop. So whatever voltage we apply, that will be dropped as IR in the winding against the resistance of the winding. So voltage equal to I into R into I, and R is proportional to N into J by I, that is from the second equation, multiplied by I. So voltage is proportional to N into J, right? So number of turns of any winding and current density, they are inversely proportional to each other from if voltage is fixed. So so this is the third important equation that we have. Another constraint is the area available constraint, or the volume of copper that is available to you, that is all that is already fixed, or that is there is some limitation there. So as soon as you have decided on the other dimensions, the volume that is available for you for putting copper, that is fixed. So volume of copper is nothing but what is the length of the copper wire into what is the cross sectional area of each copper wire. Obviously there is going to be some factors like window utilization factor and other things. That is why I put this proportional sign. Vc is proportional to L into A. Now that will be proportional to, so L is proportional to N from this Roman 1 equation, and A is nothing but I by J. So Vc is proportional to F by J, that comes out as the fourth important relationship for us. So volume of the copper, once that is fixed, so or the volume of the copper, that will have to be decided of, if F is fixed, then volume of copper and current density, they are inversely proportional to each other. That is the fourth one. Now we come to losses. We come to copper losses. Copper losses is I square into R. So I square we put as it is, and resistance is proportional to Nj by I from this equation 2. So if we manipulate it, P comes as proportional to F into J. So now let us write these important things one by one. So first thing is F equal to Ni. This is our first equation. Second equation is resistance is and this is equal to constant. This is important once B and G are fixed. Then second thing is resistance is proportional to Nj divided by I. This is our second thing. Third equation is voltage is proportional to N into J. That is our third equation. Fourth equation tells us volume of copper. Volume of copper that is required, that is proportional to F by J. That is the fourth equation. And the losses P, that is proportional to F into J. This is our fifth equation. Are these five constraints clear?
Yes, sir, clear. Sir, why we are doing this exercise? Just to know about the copper losses and what properties we need to keep as field winding, right?
So these are required. So this is from design perspective. When you are deciding what will be the dimensions, so design means you have to decide. So let me tell you. So suppose we want some flux density in the air gap, and we want the air gap. Now that means mmf is decided, mmf is fixed, F is fixed. Now you can have N1 and I1, that will give the same mmf, or you can have N2 into N2 and I2, that will also come out to be F only. So if we have F equal to fixed, then number of turns and current, they will vary like this. This is a curve for F, constant F. So you can choose any point on this curve that will satisfy equation 1. But what is the good point to choose? Should we go for higher number of turns and lower current, or lower current and higher number of turns? Or the same thing I told in two ways, higher current and lower number of turns. That is the discussion that we are having. The goal is to have a qualitative understanding about relative number of turns and current values of the armature and field winding. That is the goal, so that we can have some sense. Okay, if we have armature winding, we have some physical sense. Okay, armature winding must have lower number of turns compared to field winding. Armature winding should have higher current than field winding. What are the general trends of values, typical values? Some engineering sense about all these things. That is what we are trying to have, right? So okay,
Okay, sir, okay.
yes. So So we have all these things, we have all these constraints at our disposal. Now what is, if we decide on the current density, because once we have decided on once we have decided on the other dimensions, there's obviously some volume of copper is available to us, that is known. Say this volume of copper, once we decide on the other dimensions, then the volume of copper is also known to us, like just like this. For field winding, we have this much volume, this much area multiplied by the axial length, that is the volume of the copper that is at our disposal. For the armature winding, we have all these slot areas multiplied by the length, axial length, that is the total copper winding volume that we have, we have for our case. So one thing is, we can what is the optimal current density that we can discuss, because or we can decide, because this equation, power loss equation, tells you that we can have higher, if we have higher current density, then for realizing the same mmf, we will have higher power loss. That means, that tells you that on this curve, on this n versus I curve, if we go to higher and higher current densities, or probably that is not a good curve here, uh, probably this third, because I is not directly proportional to, I has j into cross sectional area, so that is not a good thing to discuss here. So probably third equation we will have, what is the number of turns versus j, the current density for a fixed voltage that we have. So this is the voltage equal to constant. So we can, for a fixed voltage that is available to us, if we go towards higher current density, say this point, higher current density and low number of turns, then this fifth equation tells us that we will end up with higher losses. But if we decide, if we say choose this point, say lower, very low current density but very high number of turns, then it seems to be a beneficial point, like because we are, the mmf that we want to realize, f, that is constant, so p is proportional to current density. So if we have lower current density, then our losses will anyway, our losses will be quite low. So question is, how low current density can we go? Can we, so if we can operate here, I would say 1 metal, why not there? Because that is a hyperbola. Why not operate, say, there?
But volume of the copper also matters.
Yes.
Sir, your voice is not audible.
J
Sir,
min.
sorry, your voice.
Am I audible? Hello.
Yes, sir, you are audible now.
Okay. So as soon as our V is fixed, that is whatever is the, what is the volume that we have at our disposal, that is fixed, and we know what is the mmf that we want to create, then what is the minimum current density that we can go to, that is fixed. So that is the J min that we have. So that is always another constraint. Now in this region, what is the current density that we can have? Obviously, if we have uh, area good enough area available to us, then we will obviously go to this J min point. That will end up having higher number of turns, but lower losses. That is one thing, one point clearly that we can have. Now if we compare, now if we are not here to design, I will not go through the design steps, but we are here to compare the two windings. If you look at this picture of the cross sectional area of the DC machine, so this is the cross sectional area or the area available for putting field winding, and length, axial length is same for all. So this is representative of the volume of copper for field winding, and volume of copper for armature winding is only this slot areas. Which one is bigger? Which one is more? Obviously you can see that field winding, you can put so much, you have so much volume available to you. No one is stopping you to put more and more copper into the field. So that is one thing, that is so the area available for putting field winding is quite big for you. So VC for field, that is quite big compared to VC for armature, right? So VC, if it is high, very very high compared to VC of armature, whatever is the J minimum for field, that will be quite small compared to J minimum of armature. So J minimum of field, say if it is here, J minimum of armature may be here. This is for field, this is for armature. So J minimum of field, or the J of field winding, that is typically because we finally want, once we have decided on the machine dimensions, the amount of copper that we can put, that is the maximum amount is fixed, and so that decides the J minimum. So typically that is very low, and if we fill the entire thing with copper, then we have higher efficiency, basically lower losses in the field winding. So this is a good enough point to choose for field winding. But for armature winding, the J min that we can have, that is quite big compared to the J min for field. So for arm, because of smaller area availability. So for armature, because we have lower copper volume at our disposal, so we need to go to higher current densities in order to have in order to in order to um, in order to produce the same torque, or produce um, our desired quantities like flux density in the air gap. Obviously the flux path for the two cases are very different, but this is a qualitative understanding that volume availability to us is quite big for field winding compared to armature winding. So because volume, we have so much volume available, so we want to reduce the copper losses, so we go in with the minimum J available to us. That is that this equation tells us. And for armature, we typically, because we have small area available, so we go for higher current density. That tells you that we also need to go for higher currents for armature winding. And this is just a qualitative understanding. If you want to actually do the optimization, then obviously so the copper, that will also have some cost. So finally you want to, in any design, you want to reduce cost. So that means, say copper volume, say VC, that will have some cost to it, say K1, and say some power loss if you are doing, then power loss also reduces to some electricity bill. So again some factors, say K2. So the total cost function that we have is K1 into Vc into K2 into P loss. you want to reduce, you want to minimize total loss, so you differentiate it, and you again you have to Vc is proportional to F by J, and P loss is proportional to F into J. So this equation basically comes K1 into F by J plus K2 into F into J. So K1 and F both are constant, so let me name it K3 by J plus K4 into J. So this becomes our cost function, and if we actually differentiate it and make it equal to 0, then we will have a solution of J optimum for any winding. Only thing is, this J optimum has to be higher than this J minimum, that is defined by the volume limitation that we have. So that is how generally, if it is, if these are designed well, then we will have the armature winding J to be very very high compared to the armature, or the current density of the armature winding to be very very high compared to the field winding. So that tells us that the number of turns in the armature winding will be quite low compared to the number of turns of the field winding. Field winding turns will be quite high, and the current Ia is actually going to be very very high compared to If. So if we have Ia to be very very high, then the cross sectional area of the armature winding, that will increase. You will have to use thicker wire uh, for it to pass high amount of current, and for the field winding, the cross sectional area of each wire will have to be quite small, and the length of the armature winding will be, because we have lower number of turns, then the length will reduce, and the length of the field winding LF, that will increase. Now what does this tell you? Armature winding resistance, that is proportional to LA by AA. So for armature winding we have higher cross sectional area, this is big, and LA to be quite small. So LA is quite small and AA cross sectional area is quite big. On the other hand, RF, we have RF proportional to LF by AF. LF to be quite big because we have a lot of turns, so length is quite big, and AF is quite small because we need not carry a lot of current, so current density is quite low. So this tells you that the overall RF, the armature, the field winding resistance, because LF is higher and AF is lower, so the RF will be quite high. On the other hand, LA is lower, AA is higher, so overall armature resistance will be quite low. So if you pick out any practical DC machine parameters like the armature winding resistance, field winding resistance, you always will find that armature winding resistance is very very small compared to the field winding resistance. I just wanted, I tried to describe qualitatively why it happens that way. On the other hand, let us now go back to the inductance, self inductance of the field winding and armature winding. So what is the self inductance of the field winding? That is number of turns of the field winding square the field winding reluctance. And what is the armature winding self inductance? That is number of turns of the armature winding square divided by the reluctance of the armature winding. From the study of the magnetic path for these two coils, already we have seen that RF is very very low compared to RA, that tells us that 1 by Rf is very very high compared to 1 by Ra. Now additional to it, Nf is also very very high compared to Na. So if we get this, if we so Nf square is very very high compared to Ns square. So if we multiply these two, Nf square divided by Rf, that will be very 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 high compared to Ns square divided by Ra. So that means the field winding resistance will be very high compared to the field winding inductance. Typically if you look at some values, the field winding inductance may be in few henries or tens of henries also. So it may be 10 henry, but armature winding resistance may be only few millihenries, so 10 millihenry, 20 millihenry, 50 millihenry. It will be in the order of 50 millihenries, whereas field winding inductance may go as high as henries also. So this Lf by La, this whatever is the relative ratio, that is, you can see that this is Henry, this is millihenry. So big difference between the two. But if you pick out some values, say Ra may be few ohms, fraction of ohms to a few ohms at max, so zero point 0.2 ohm, zero point 0.1 ohm, 0.5 ohm, somewhere in that range. The Rf may be 200 ohm, 250 ohm, 150 ohm, like that. So say 200 ohm. So the relative difference, so you can then compare the time constants. If you compare the time constants, you will find that uh, the armature winding time constant is quite low compared to the field winding time constant, the typical values. So this is another. So first thing that we have discussed is that relative values of the inductances Lf and La. Next thing is relative values of the resistances of the two windings Ra and Rf, and next thing is the relative values of the time constants. So what is the meaning of time constant? So if we have, say I am indicating here only, if you have some field voltage and field current, say field current is red, field voltage is blue, you had field voltage to be 0. Now if increase the field voltage suddenly, now you expect the field current to also rise. Similarly, you have armature voltage and armature current. So armature voltage is initially 0, and at the same instant you increase the armature voltage, you give a step to that. Now if the time constants are very different, then field may rise like this, very slow, but armature may rise like this. So that is the relative difference. So that is why if we want to control the torque equal to K into phi into Ia, and again phi is proportional to If, so K1 into If into Ia. If we want to have good response time in torque, it is better to control armature current compared to field current, because field current, even if we change, because we are changing the currents by changing some voltage, we can change voltage instantaneously, or almost, if we like, if we use power electronic converter, we can do that instantaneously very quickly. But current, at what pace it will increase or decrease, that is not up to us, that depends on the voltage, that depends on the time constants. So time constant, the relative values tell you that armature circuit time constant is very very low compared to the field winding time constant. So that is why if you want good dynamic performance of torque, you want torque to rise very quickly, then it makes sense for you to control the armature current rather than the field winding current, right? So um, yeah, I think we can stop here. So we have discussed about we have discussed some design constraints, and uh, last day we tried to discuss from another perspective, which is more like uh, the advantage that comes to us, but that comes from these design constraints and the design choices that we need to make. So if you actually have this cost function, C, finally you have some K3 into, what was that, K3 by J plus K4 into J. You have some cost function which you want to reduce. So your only variable is J. Only parameter that you can vary is only thing that you can decide what is the what you want to optimize, that is the current density. So you have to differentiate the cost function C with respect to the current density. What you will have is K3 into minus of 1 by J square plus K4, that you need to push it to 0. So if you push it to 0, then you have K4 equal to K3 into 1 by J square. So J square equal to K3 by K4. So J is equal to under root of K3 by K4. That is the optimal J that you can have if you want to reduce cost, because as I have indicated here, this minimum J is from the maximum available copper area, maximum volume of copper volume that is available to us. But copper also has some cost. We cannot blindly put more and more copper because copper is expensive. So if we actually want to optimize, then we should take a factor, say volume of copper, and that there is some cost per volume, and power loss, there is some cost per watt, some rupees per watt, that is electricity loss. So finally it is in terms of rupees. You want to reduce the rupees, you want to have some uh, have some optimization, this thing variable, which is J, the current density in this case, because all this VC and P loss that can be expressed in terms of J, because F is the mmf that we want. We cannot reduce it or increase it because that is on our requirement. We cannot say no to our requirement. We have to make the requirement, meet the requirement. So this becomes our cost function, and if we differentiate the cost function with respect to the current density, that then we can have and make it to 0, then we end up having this thing J optimal equal to under root of K3 by K4. And how to understand it is minimum cost or maximum cost, because it is only telling you that either C is being minimized or C is being maximized. So if you double differentiate the same cost function, that is if you differentiate this thing, then you will have, again you will come back with plus sign K3. So minus 2 will come out, and you will have J cube. This minus will be there, so this minus and minus, they will make it finally plus. So it is some positive value because J is always positive. So at this J optimal value, the second derivative is actually positive. That tells you that C is being minimized here, right? So that is the optimization problem, that tells you that for getting the same mmf, which size should you choose? Should you choose higher current density and lower uh, lower number of turns, or you should go with lower current density and higher number of turns. That is the optimization that we discussed today. So next day we will start understanding about the electromotive induced EMF in any magnetic circuit, and then we will understand why induced EMF is there in the field winding, not in the field winding, why on the armature winding, and what is the nature of that induced EMF. Is it induced EMF due to self inductance, or is it due to mutual inductance? We'll understand all those things, and we'll continue it on the coming Friday. Okay. Do you have any question?
No, sir.
Okay. Things are clear.
Yes, sir. Clear. If I have any after watching the video, we'll post in the group.
Okay. Sure. Sure. Thank you.
Thank you, sir.